Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 4 on function notation. So functions, which are the basis of much of this course, we started discussing in our last lesson, right? And all they are is a rule that takes an input and converts it into exactly one output. Now functions have their own notation. Notation in math just means a way to represent something. Like when we have like a line like this and a line like this for a little symbol like that, and that notation means to take the two numbers sitting on either side of them and add them together, right? It's just that you've been using that notation for such a long time that it's natural for you. Well, function notation will be used in this course and every course from here until you're done with math. So let's start taking a look at it. All right, since functions are rules that convert inputs to outputs, it makes sense that they have a notation that shows the input, the rule, and the output. But the notation takes a little practice to get used to. So right now, I'm going to show you how the notation works, and then we'll get practice on it all throughout this lesson. Exercise number 1. For each of the following functions, find the outputs for the given input. Okay, so let's take a look at letter A, right? We see this f with a little parentheses and an x and a parentheses equals 3x plus 7. It looks a lot like we have a variable f that's multiplying the variable x, right? Because that's typically what parentheses mean, right? They typically mean multiply, but they don't here. Basically, f is just the name I'm given the function, so it's called the function f. And I actually read this as f of x. F is a function of the variable x, and the rule is 3 times x plus 7. So when I see f of 2 equals, what that's telling me is that I want the function output when the input is 2, and then all I have to do is take my input and put it into the rule. So in other words, f of 2 is 3 times 2 plus 7, which is 6 plus 7, so f of 2 is 13. That's it, right? The rule is sitting right here. What we call the function is this letter. Oftentimes functions are called something descriptively, but if they're just sort of like mathematical functions, we typically use letters that are somewhere, in the range of f, g, h, k, something like that. Again, don't get me wrong, if you've got like, let's say velocity, right? We might use v as the name of the function, okay? But that's basically it, right? Here's the rule in equation form. Sometimes we won't have the rules in equation form. We'll get to some of those a little bit later on. But here's the rule, here's the input, and this is asking us for the output. So when it says f of negative 3 equals, all I'm going to do is put negative 3 in for the input and work through the rule. That's negative 9 plus 7. So f of 3 is equal to negative 2. That's function notation. That's basically it. So pause the video now and see if you can evaluate both the function g in letter B and the function h in letter C, given the inputs 20 and 0 in this function and 8 and 0 in that function. Pause the video now and see what you can do. All right, let's do it. So g of 20. Well, what does the rule say? The rule says take the input, subtract 6 from it, and divide by 2. So that's going to be 14 divided by 2, which is an output of 7. On the other hand, if the input is 0, I'll take 0 minus 6 divided by 2. 0 minus 6 is negative 6, and negative 6 divided by 2 is negative 3. Okay? And again, all I'm saying is when the input is 20, the output is 7. When the input is 0, the output is negative 3. That's it. Now this particular function has a square root involved, which, maybe we need a little bit of work on. Right? Let's take a look. When the input is 8, right, the output is going to be the square root of 2 times 8 plus 9. All right, 2 times 8 is 16 plus 9. That's the square root of 25, and the square root of 25 is 5, right? 5 times 5 is 25. Likewise, when the input is 0, the output will be the square root of 2 times 0 plus 9. 2 times 0 is 0. So that's going to be the square root of 0 plus 9, which is the square root of 9, which is 3. Okay, so I really want to emphasize something because this is maybe the trickiest thing when you first experience or see function notation. This looks a lot like f times x or g times x or h times x, but they're not. All right, the small letter here, f, g, and h, is literally the name we're giving to the function. The parentheses here is just there to show us what the input to the function is. That's it. Okay, it has nothing to do with multiplying the variable f, let's say, by the number 2 or by the number -3. Totally irrelevant. All right, let's keep working with function notation. When functions and rules are given by algebraic equations, function notation is helpful in showing the rule and telling us what the input is, right? You'll often see things like y equals f of x, because remember, right, the output to a function is always the y coordinate in an xy coordinate pair, okay? But then there's the rule, and then whatever is sitting inside of those parentheses is the input. Well, let's take a look at another situation where we have a function defined by a formula. Exercise number 2. A function is defined using the following formula. F of x equals x divided by 3 plus 7. Letter A, explain what the function rule does to convert the input into an output. All right, remember, functions convert inputs into outputs. This takes us all the way back to Unit 1, Lesson 1. Because the function rule is really just given by that expression. And what does that expression do to x? It divides it by 3 and then adds 7. Right? That's it. Divides by 3, then adds 7. Divides by 3, then adds 7. All right, even just knowing that verbal description, we could then evaluate f of 6, the function at 6, an input of 6, and f of -9, right? And again, all we do to do it, let me do f of 6, and then you can do f of -9, right? F of 6, I'm going to take my input, I'm going to divide it by 3, and I'm going to add 7. So that's going to be 2 plus 7, and that's going to be an output of 9. All right, so when the input was 6, the output was 9. You figure out the output when the input is -9. Pause the video now. All right, let's do it. So simple enough. When I put in -9, I'll get -9 divided by 3 plus 7. -9 divided by 3 is -3 plus 7. And -3 plus 7 is 4. Okay, now very important. Let's take a look at letter C. What 2 coordinate points would lie on the graph of this function based on your answers to B? So this is absolutely critical. We always want to be thinking a little bit about how inputs and outputs to functions then would get translated to the graphical representation of a function. Never forget that the input, right, the thing that's sitting inside of these parentheses is the x coordinate. There it is, right? It's called x right there. And the output is the y coordinate. So the 2 coordinate pairs that must lie in this graph based on what we just did are 6, 9 and -9, 4, right? The input, x equals 6, gives an output y equals 9. An input of x equals -9 gives us an output of y equals 4. Now, what's kind of cool is that we can have functions whose rules are based on other functions. Let's take a look at one of those in letter D. If g of x equals 2 times f of x minus 1, then what is g of 6? Show the work that leads to your answer. Well, again, one of the great things about function notation, right, is it just basically says this, right? If I want to know what g of 6 is, then what I'm going to do is anywhere in this definition that I see an x, I'm going to replace it with a 6. Okay? Now, the only place in this definition of the function g of x, in this rule for g of x, the only place there's an x is sitting right there. So that says that g of 6 is 2 times f of 6 minus 1. Okay. One of the most important principles in all of math is that equals can be substituted for equals. So in other words, you might look at this and go, well, I'm not sure what I'm supposed to do right now, except we know what the value of f of 6 is. F of 6 is equal to 9. There it is, right? F of 6 is equal to 9. So now I can say, since g of 6 is equal to 2 times f of 6, then that must be 2 times 9 minus 1, which is 18 minus 1, which is 17, right? And really, what does the definition, what does the rule for g of x state? The rule for g of x states at any input value, what I'd like you to do is take 2 times the output of f for the same input value, and then subtract 1. And since I knew what the output to f was when the input was 6, all I had to do was multiply that output by 2, giving me 18, subtract 1, and giving me 17. Now, one of the trickiest things of all for students is a problem like at letter E. Let's take a look at that. Find the value of the input for which f of x equals 12. Show your work. Now, I wouldn't fault almost any student at this point who looked at this question and said, oh, I'm going to take 12 and I'm going to plug it in for x and I'm going to figure out what the output is. Because that's what we've been kind of doing this whole time. But notice this question says, find the value of the input, right? We want to find the value of x for which f of x equals 12. This is the output, right? So they're actually giving me the output, and they want to know what the input is that will give that output, right? That is always a trickier thing for functions, right? A function rule should be pretty easy to take an input and give an output, because that's what functions do. They take inputs and they give outputs. What's much more difficult is sort of running the function backwards and saying, hey, look, I'd really like to know the input that gives me this particular output. And in fact, the way that we have to do this right here, right, is we have to take the rule for the output, right, x divided by 3 plus 7, and we have to set it equal to that output, right? That is the rule, right? How do I get an output? Well, I take the input, I divide it by 3, I add 7, and I get my output. So if my output is 12, if f of x, that's my output, is equal to 12, what's my input? Well, now I just solved this equation, right? I mean, this is, take me back to the last unit, please, right? I'm just going to subtract a 7 from both sides. That's going to give me x divided by 3 is equal to 5. Then I'm going to multiply by 3 on both sides, and I'm going to get x equals 15, right? But again, think about the work I have to do for that. In order to actually come up with the value of a function, right, like I did in letter B, to come up with values of functions, I just have to evaluate an expression. Take a value of x, plug it into an expression, do some arithmetic, and get a value out. To actually find the input that gives a particular output, which is what I did in letter E, I actually have to solve an algebraic equation, which is much more difficult. Maybe not much more difficult in this case, but a little more difficult. All right, so let's keep going and do more with function notation. Even when there's no equation involved, function notation can still be used to specify an output for a given input. And again, functions are used all the time in the real world. Let's take a look for the first time at a function given in a table form. Exercise number 3. Boiling water at 212 degrees Fahrenheit is left in a room that is at 65 degrees Fahrenheit. Temperature readings are taken each hour and are given in the table below. In this scenario, the temperature, T, is a function of the number of hours, H. All right, and let's talk about this for a second. This is a great example of a real-world function, right? Because for any given amount of time or any given number of hours, there is only one temperature that that liquid is at. It's not like I can come to you and say, hey, how hot is the temperature now? And you're like, well, it's 98 degrees, or 72 degrees. Your choice. Take your pick. No, it's going to be one and only one temperature. Okay? Now, we can still ask the same kind of questions like evaluate T of 2 and T of 6. But what does it mean to evaluate T of 2? Well, again, that is the input, right? And almost always, when you have a function represented in table form, if the function is in a horizontal table, the first row is the input and the second row is the output. If it's a vertical table, then it's the sort of column on the left that's the input and the column on the right that is the output. And we'll see some of those too. But when it says evaluate T of 2, well, I go to an input of 2, I look what the output is, and it's 104. And specifically, it's 104 degrees Fahrenheit, right? It has units, right? And basically, we can interpret that as saying, well, at 2 hours, the temperature of the liquid is 104 degrees Fahrenheit. So why don't you pause the video right now and write down the value of T of 6. All right, well again, T of 6 is just asking us for the output when the input is 6, and that's 68 degrees Fahrenheit. Simple. Now let's take a look at letter B, where we reverse it a little bit. In letter B, for what value of H is T of H equal to 76, right? In this case, I'm not giving you the input, I'm asking you for the input. What I am giving you is the output, right? And we have to recognize that. If the number that's given is inside of the parentheses, we've given you the input. If it's what the function is equal to, we've given you the output. Pause the video now and see if you can give me the input value for when the output value is 76. All right, well, pretty easy. Where is there an output of 76? Right there. So that means H is equal to 4 hours. All right, for an input of 4 hours, the output is 76 degrees Fahrenheit. One final one on this, right? Letter C. Find the value of T of 8 minus T of 0. Using proper units, give an interpretation of this answer in the context of the problem. All right, this is very important. We will use function notation oftentimes in larger calculations, okay? And this is a good example of one. So before I even do the T of 8 minus T of 0, let's write down what those two things are. T of 8, right, is 65. And I'm going to throw some units on here. T of 8 is 65 degrees Fahrenheit. T of 0 is 212 degrees Fahrenheit. So T of 8 minus T of 0 is going to be 65 minus 212. Now, let's pause just for a second. I'm going to do this without my calculator, but of course, feel free to use your calculator at any point in this course to do sort of this type of arithmetic. Keep in mind, though, we have a smaller number subtracting a larger number. So that will always, anytime you ever have a smaller number minus a larger number, you will always get a negative answer. And in fact, here I get negative 147 degrees Fahrenheit. So that's T of 8 minus T of 0. The question asks us to calculate that, and that's the answer to that calculation, but it also asks us to give an interpretation of our answer in terms of the problem itself. So how could you interpret that? Pause the video now and think about it a little bit. Well, what we're really doing here, right, is we're finding the difference between the temperature after 8 hours and the temperature right when the liquid was at boiling at 212 degrees Fahrenheit. And because it's negative, what we know is that the temperature decreased or went down. Specifically, we can interpret this as the liquid's temperature decreased. It's very important, decreased or went down or got cooler. The liquid's temperature decreased by 147 degrees Fahrenheit over the first 8 hours. Right? The temperature went down by 147 degrees over the first 8 hours. That's how we can interpret that change. And we're going to see this a lot, where we take a function's value at one input and we subtract a function's value at another input to see if the outputs either went up, if that change is positive, or went down if that change is negative. More on that in the future. Function notation can certainly be used when the function is given by a graph and there's no equations or no tables or anything, okay? The thing that's important to always remember is that the input is the x and the output is the y. So, knowing that, let's do exercise number 4. The function y equals f of x is defined by the graph shown below. Answer the following questions based on this graph. Letter A, evaluate f of 2, f of negative 3, f of 5, f of 7. All right, let's talk about how to do this. It takes a little bit of practice, but it's actually really pretty easy, maybe even easier than it was with either the table or with the equation, right? When I see something like f of 2, what that 2 is telling me is that that is an x coordinate, x equals 2, right? So what do? I come over to the graph to x equals 2. All right, and then I go up and I find a point on the graph right here that's got an x-coordinate of 2, right? So when the x-coordinate was 2 on the graph, the y-coordinate was 9 and only 9, right? And it could only be one y-coordinate for that x-coordinate, or this wouldn't even be a function. So f of 2 is equal to 9, right? That's it. Let's do another one and then have you do a couple of them on your own. Let's take a look at f equals 5, right? For f equals 5, I'm going to go over here to an x-coordinate of 5. I'm going to go up to the graph. That's the point 5, 6, and therefore f of 5 is equal to 6. That's it. All right? All I'm doing now is saying, look, I'm giving you the x-coordinate on the graph. What's the y-coordinate? Why don't you figure out what f of negative 3 is and what f of 7 is? All right, let's do f of negative 3. Let's go over here to negative 3, go down, not very far. That's the point negative 3, negative 1, and therefore the output is negative 1. F of 7 might be a little bit tricky because when I go over to f of 7, I'm right here. And that's the point 7, 0, so f of 7 is just 0. Okay, so when I give you just evaluate the functions, when I give you the inputs, asking you for the outputs is pretty easy. I'm giving you the x-coordinate, you just go ahead and find the y-coordinate. But just like in previous problems, we can kind of flip this on the head and we can give you the outputs and ask you for the inputs. Now before we get into those, let me try to just erase these things instead of moving them all over the place. Okay, so let's take a look at letter B. Solve each of the following for all values of the input x that make them true. All right, so this is kind of cool, right? Here I've got f of x equals 3. Now I'm saying to you, that's y equals 3, right? So I want to find any x value that has an output of 3. Here's the easy way to do that. Very similar to what we did before. I'm now going to go up to y equals 3, and I'm going to kind of look like for any points on this curve where the y value is 3. So here, there's one at -1, 3. Here's one at 6, 3. And here is one, this one's a little bit trickier, at 8.5, 3. And therefore, x equals -1, x equals 6, and x equals 8.5 all solve that equation. Every one of these inputs, if you plugged it into the function, would have an output of 3. Why don't you pause the video now and try to find all the inputs that have an output of 7. All right, I'm going to do exactly the same thing, right? Again, this is a y value of 7. So I'm going to go up here to 7. All right, just draw a horizontal line in. Those are going to be all the same y values. Here's 1 point. Here's 1 point. This is at 1, 7. This is at 4, 7. And so x equals 1 and 4 both solve that equation. That's it. Let's take a look at one more issue with this and then wrap the lesson up. Remember, we talked about functions as being rules that converted numbers, typically, that are sitting in a domain set, right, into numbers that are sitting into a range set. Let's take a look at letter C. State sets using set builder or interval notation, whichever you like, for the domain and the range of this function. Well, again, a lot of students early on, and this is very understandable, will say the domain is the x values, right? So I look at this function, right, and I want to know all the x values that live on it. Well, I can think about that a little bit by saying, well, the smallest x value here is an x of -4. And the largest x value is an x of 9. So my domain in interval notation would be -4, 9, and both of those are included. If I wanted to use set builder notation, I would have like the squiggly brackets, and I'd say all real numbers such that x is greater than or equal to -4 and less than or equal to 9. But I'm going to use interval notation because it's quicker. All right, the range, right? The range are the y values. And these tend to be a little trickier, okay? Because of the difference between inputs and because of the difference between inputs and outputs on a function, right? Inputs are simple. You can just go kind of like to the most left on the graph. That's the beginning of your domain. Go to the end of your graph, right? And that's the end of your domain. Y values, I really kind of want to think in this direction. So I kind of look like this, right? That's my lowest y value, and that's down here at -3. And my highest y value is up here at +9. And I certainly hit every y value between -3 and 9. And so my range is that interval, -3 to 9. And that's it, right? Again, what we want to do is we want to start just getting used to this terminology, domain and range, right? All the values in this interval will have an output somewhere in this interval. All right, let's wrap this up. So today what we did is we looked at what was called function notation, f of x, f parentheses x parentheses, right? And it's just a convenient way to say, here's what the input is, here's what the rule is, tell me what the output is, or, you know, here's the function, here's the output, what are the inputs? Okay, function notation will get used a lot, obviously, when we look at functions. It won't be used every time we look at functions, but most of the time it will. Get a lot of practice on it on the homework, understanding how to use it when you've got a formula, when you've got a graph, when you've got a table, right? It always works the same. The number inside of the parentheses is the input or the x-coordinate, and the thing that the function is producing, the thing that the function is equal to, that is the output or the y-coordinate. All right, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.